Today's lecture, I'm going to focus on two natural resources that you have spent much of the semester through discussion working on in the modules. First, I'm going to discuss wind, and second, I'm going to discuss solar. Wind forms on the Earth simply because incoming solar radiation, or sunlight, enters the Earth's atmosphere, warms up the Earth's surface, and all of the incoming radiation from the sun, if you think of that as shortwave radiation, and of course it's got a range of wavelengths, but if you imagine that as only shortwave radiation, what happens at the Earth's surface is that some of that radiation is re-radiated as long-wave radiation, and that warms the air directly above the surface, and that warm air then ascends because it's more buoyant than cold air. And as warm air from the surface ascends, it moves through the atmosphere because the Earth rotates and the atmosphere convects, and that warm air will displace cold air that descends or sinks to the surface of the Earth. So when you look at these turbines here that have the blades that are rotating in moving wind, that is how wind is created at Earth's surface within the atmosphere. In terms of harnessing the energy in wind to produce electricity, we build what are called wind turbines. And I'm going to show you a video now that walks through the details of how wind energy is captured and how it's converted to electricity.
Windmills have been assisting mankind to convert the energy contained in wind to many other useful forms for the last 2,000 years. Today's wind turbines are capable of converting a great amount of energy in the wind into electricity. This is due to the blades, which are developed using state-of-the-art aerodynamic analysis and the other performance-enhancing equipment. In this video, we will explore these different sets of technology in a simple yet scientific way. First, let's get into its basic working. If the blowing wind can turn the wing, we will receive electricity from the generator that is attached to it. However, how does the blowing wind turn the wing? Let's have a close look at the blade. The blade has a lot of airfoil cross-sections consisting of different sizes and shapes from the root to tip. The simple airfoil technology makes the wind turbine blade turn. That means that a lift force is produced when a fluid moves over an airfoil. This way, the wind turbine achieves the basic rotation we are accustomed to seeing. Just as in a moving train, you experience things relatively, the moving wind turbine blade also experiences the wind relatively. For the moving blade, the relative wind velocity is as shown. Therefore, the wind turbine blade is positioned in a tilted manner in order to align with the relative wind speed. As the blade velocity increases to the tip, the relative wind speed becomes more inclined towards the tip. This means that a continuous twist is given to the blade from the root to tip. However, this rotation cannot be directly coupled to a generator because the wind turbine blades typically turn at a very low rate of RPM due to the issues of the noise and mechanical strength. Considering this slow speed rotation, we cannot produce any meaningful electricity frequency from the generator. So, before connecting to the generator, the speed is increased in a gearbox. The gearbox uses a planetary gear set arrangement to achieve the high-speed ratio. A brake also sits in the nacelle. The function of the brake is to arrest wind blade rotation during excessively windy conditions. Consequently, the electricity that is produced is transferred through the cables towards the base, where a step-up transformer is situated. The wind turbine should face the wind normally for maximum power extraction. But the wind direction can change at any time. A velocity sensor fitted on the top of the nacelle measures the wind speed and direction. The deviation in the wind's direction is sent to an electronic controller which in turn sends an appropriate signal to the yawing mechanism to correct the error. You can see how the yaw motors turn the nacelle. Thus, the wind turbine will always be aligned with the wind direction. According to the wind speed, the relative velocity angle of the wind also changes. A blade tilting mechanism tilts the blades and guarantees a proper alignment of the blades with the relative velocity. Thus, the blades are always at the optimum angle of attack with the relative wind flow. Efficiency of a wind turbine is a really interesting topic. To gain a good insight into wind turbine efficiency, assume that you are measuring wind speed at upstream and downstream of a wind turbine. You can note that the wind speed at the downstream is much smaller than the upstream. This is because the blades absorb some kinetic energy from the wind. The same amount of energy is converted as mechanical power of the wind turbine. It is interesting to note that a wind turbine absorbs 100% of the available kinetic energy only if the downstream wind speed becomes zero. However, zero wind speed at downstream is a physically impossible condition. This cartoon animation clearly depicts this fact. Zero downstream speed simply means that the whole flow is stuck. This physical reality of the flow demands a certain amount of exit wind speed. That means that there is a theoretical maximum efficiency a wind turbine can achieve. This limit is known as Betz's limit. Essentially, it means that no wind turbine in the world can ever cross the efficiency limit of 59.3%. We hope you have now developed a good insight of the operation of wind turbines. Thank you.
So I'm not going to hold you to everything in that video. I'm going to turn the sound off and just highlight a couple of things. When the video talks about the wind turbines being placed in a direction normal to incoming wind, think of that as at a right angle to the incoming wind. So if we move back through the video and I get to that part, I just want you to imagine the wind is coming in from the front of the wind turbine and the blades are at a 90-degree angle. The second thing here that's important about wind turbines is what they call the step-up speed. So whatever the speed of the blades are that are rotating, there's a gearbox inside the top of the wind turbine in something called the nacelle, which is the actual part on top that contains all of the instrumentation. And that gearbox increases the speed of the turbines by about an order of magnitude. So let's say the speed of the turbine blades is roughly 10 miles an hour. The gearbox increases the speed to about 100 miles an hour inside the nacelle. There are lots of parts inside the top of the wind turbine, the nacelle, that are not relevant for this class, so I'm not going to hold you to those. I just want you to picture here on the right-hand side of the screen a commercial scale wind turbine. And to get a sense of the size, a wind turbine where you can see the bottom ground level surface here, when the blade, one of the three blades, is perfectly vertical, so it's parallel to the base of the wind turbine, it stretches from the back of a football field to the other end zone of a football field. So it's give or take 100 to 110 meters in total height. Now, what's critical about converting the energy in moving wind in the atmosphere to electricity is that we're harnessing the kinetic energy of wind. Now, kinetic energy of wind is determined by this equation here, 1/2 mass velocity squared, and the mass here is the mass of air. And it's common that we don't think of air as having a mass, but in fact it does due to all of the dissolved gases in air. So at sea level, the density of air is approximately 1.2 kilograms per cubic meter, where a cubic meter is a box about 3 feet by 3 feet by 3 feet. And because air has a density, it therefore has a mass. So when we think about converting that converting that kinetic energy, or really capturing that kinetic energy to produce electricity. If we look at a commercial scale wind turbine, I've circled here the diameter of a circle that I've drawn around the 3 blades, and then we see that diameter here in yellow. So we've got this circumference here and then the diameter across the center, and the area of this circle is equal to pi times the ratio diameter divided by 2, or radius, squared. So that cross-sectional area is the area that the 3 blades sweep as the wind is moving them in the atmosphere. There are a number of other equations here that I'm not going to hold you to, but I'll walk through just so you can understand how that kinetic energy of air is harnessed to produce electricity. In a particular time t, the mass of air that passes through the area is given by this equation. So the mass is equal to the density of the air times the cross-sectional area that the 3 turbine blades sweep times velocity times time, and again where rho is the density of the air. And if we combine the formulas that I've shown you here and in the previous slide, you can calculate the energy captured by this equation: density times cross-sectional area times the cube of the velocity times time divided by 2. Now what's critical here is the density of air, which changes as a function of position at sea level, and then at higher elevations the density decreases. Engineers can control the cross-sectional area because that's what we fix based on the length of each of the blades as they sweep through the air. And then notice the velocity of wind is cubed in this equation. So the velocity of wind in this equation plays the most important role in producing energy. And we can use this energy per unit time to actually calculate power in watts, something you've worked on in the modules where you've dealt with kilowatts and megawatts and gigawatts. And what we find is power per unit time is equal again to density times cross-sectional area times the velocity of wind cubed divided by 2. This tells us that the faster the wind is blowing, the more power we can produce per unit time and over an integrated amount of time. One of the things that engineers do when they are siting wind energy infrastructure is they make measurements, often for several years in a particular area, using an instrument we call an anemometer. And an anemometer measures wind speed and wind direction simultaneously. That's all captured digitally now, so you know by the second, every minute, every hour, every day, every week, every month, over a number of years, how the wind speed varies both in terms of speed and direction, meaning the upstream direction. And one of the things that you can see here on this graphic is the tower height, meaning the top of the nacelle, and the wind speed is on the right y-axis. And what we know is if you look at the x-axis, we can calculate the increase in wind power as a function of the height of the tower and the corresponding wind speed. So as the towers get higher or taller above the Earth's surface and wind speed increases, the wind power, meaning the amount of electricity that we can harness, increases with tower height. Now all of the words on the right hand side over here are just meant to emphasize that wind density of air changes as a function of temperature, and so geography also plays an extremely important role. And the text here at the top, this relates to the fact that there is this V cubed in the equation, and if we read the text, the power output from a wind turbine is a function of the cube of the average wind speed. And again, that's the velocity cubed here. So in other words, if the wind speed doubles, meaning that the wind speed increases by only a factor of 2, the power output increases by 8 times. So if the wind speed increases by 2 miles an hour, 2 cubed is 8, so the power output increases by 8. If the wind speed increases by 4 miles an hour, 4 cubed is 64, so the power output increases 64 times. You've looked at the map on the right-hand side of the screen in one of the earlier modules when you figured out how much electricity you could generate by siting wind turbines across the lower peninsula of Michigan. And I just want to highlight that when you look at the state of Michigan, where the colors, if we look at the legend, correspond to wind speeds, and remember, power increases as the cube of the wind speed or velocity, here given as meters per second. The ideal location to site wind turbines is the location that has the highest average sustained wind speeds. So when we look at the state of Michigan, you can see here Lakes Huron, Lake Michigan, Lake Superior, all of the coastline and areas within a few tens of miles of the coastline, they have the highest sustained wind speeds. So these are the areas that are targeted for wind development. If you look at the areas in yellow, so for example here in the lower right we have Detroit, much of the area to the northwest and west of Detroit has very low sustained wind speeds, and so that's why we would never build wind parks here in this area of Detroit. We would build the wind turbine infrastructure along coastlines. And we see the same thing when we look at the map of the United States on the left side of your screen. If you look at the legend for this figure, where we've got at the bottom the various colors, you can see that they correspond to different wind speeds, where blue in this case are the highest wind speeds, give or take 20 to 25 miles per hour. And you can see along the eastern coast here of the United States, lots of blue. You can see Lake Michigan, Lake Superior, lots of blue. And then you can see over much of the west coast, central and northern California, Oregon, and Washington, lots of blue. And you certainly see lots of green. And I highlight also lots of green in the Rocky Mountain region and the Great Plains states here. So wind energy potential is not equal everywhere. For example, if we look at the southeastern United States, we can see wind energy potential off the coasts of the South Carolina, Georgia, Florida, across into the Gulf of Mexico towards Louisiana and Texas. But notice that eastern Texas and these Gulf states have very low sustained wind speeds. Only when we get into West Texas, up into Texarkana, Oklahoma, and then the northern Great Plains states do we see wind speeds that are high enough for wind energy development. So which states are the leading producers of wind electricity? This is something that may surprise you, and I'm going to play a map here, and before I hit the play button, I want you to think about election results. So I know I have people who are listening to the lecture who are not U.S. citizens and did not vote in the last election. But as I play through the maps, what you're going to see is at the top will be the year, and this is the installed wind power capacity in megawatts. It's giving us a sense of how many wind turbines are installed on the ground and how much total wind electricity is being produced across the United States. The legend here shows you colors for that wind power capacity. So colors here in blues will have the most wind capacity, and then the lighter colors down to these light yellows will have the least wind capacity. And notice what happens if we start in 1999. Where do you see wind capacity installation increasing the fastest? I mentioned in the last slide that many of the states in the U.S. Southeast do not have high average sustained winds, but the states in the Rocky Mountains and Great Plains regions do. There are significant sustained wind speeds off the Pacific coast, California, Oregon, Washington. I also mentioned the Great Lakes, Lake Michigan, Lake Superior. So as this plays through from 1999 to the year 2020, notice the Great Plains states here. And the point I want to make is that these are states that overwhelmingly voted Republican in 2016. And if you read literature from social scientists who canvass knocking door to door, asking people in each state across the country their personal opinion or their perception of wind energy, you'll find that most of the people, or a majority, more than 50% of the people surveyed in the Great Plains states, are opposed to renewable energy, which begs the question, if a majority of people in this part of the United States are opposed to renewable energy, why is so much renewable energy in the form of wind being built there? So here are the election results from 2016, and these are the 5 leading U.S. wind states as of August 2016. And I just want to highlight North Dakota, Oklahoma, South Dakota, Kansas, and Iowa. In red are the proportion of voters who voted Republican, and in blue are the proportion of voters who voted Democratic. And again, the point I want to make is that these are states where when you ask what public opinion is for renewable energy, overwhelmingly a majority of the residents of each of these states say that they are opposed to renewable energy, but the actual facts tell us something different. They tell us that each of these states, if we go back here and look at the amount of renewable energy in each of these states, these are states that dominate wind energy production in the United States. And the reason for that, well, skipped ahead too fast. The reason for that is cost. So this is a table that you've seen in one of your recent modules, and I've highlighted here the cost for wind. One of the columns here I didn't have you explore in the module is known as capacity factor. Capacity factor is a percent of the amount of time over an entire 365-day year when each one of these electricity technologies produces electricity. Now, wind, in terms of wind turbines, has capacity factors of between 40 and 45%, meaning that over the course of an entire year, about 40 to 45% of the time, there is enough wind at a suitably high average speed that wind turbines can be spun to capture that kinetic energy of moving wind to produce electricity, meaning that 50 to 60% of the time, wind turbines are not able to capture electricity. Now, this is not a human error. This is simply the fact that the wind does not always blow. So on average, across the United States, where these data were generated, wind turbines are spinning 40 to 45% of the time. If you compare that to these fossil fuel technologies up here, or advanced nuclear here, you can see advanced nuclear operates 24/7, 365, about 90% of the time. You can see advanced combined cycle, this is a natural gas plant, 87% of the time. And different types of coal plants operate with an 85% capacity factor. These types of electricity resources we think of as baseload power, a term I introduced when talking about hydroelectric. Wind as it exists right now, wind is not baseload power, but it is inexpensive. When we look at onshore wind, it is cost competitive now with all forms of electricity generation. It is cheaper than oil, it's cheaper than coal, and in much of the United States now, it's cheaper than natural gas. So economics have led to the significant growth of wind energy development. So now I want to give you some high-level insight into solar energy. Again, something that you have focused on in some of your earlier modules, and in one of your summaries you were asked to describe the basics of how solar energy works. And all we have here is, again, incoming solar radiation or insolation, where with wind that sunlight heats up the ground surface and causes air molecules to absorb energy that's being re-radiated from the ground surface. In this case, we have what we call photovoltaic or PV solar cells, and these PV solar cells absorb photons from the sun and convert those to electricity that flows out of the back here via wires, and we can power our lives using the electricity that flows in those wires. There are different types of solar energy. Among them, we have solar heating for residential systems, where we might have solar panels on a roof and they're simply capturing energy and using that to warm water that we might consume in the house. And what I'm going to focus on here is solar electricity, photovoltaic, and something also called concentrating solar power. In terms of solar heating, it's becoming extremely popular around the world because it represents a way to harness free energy in the form of the sun's incoming solar radiation. Here we have the Burj Khalifa, one of the tallest buildings in the world. If not, I think it's the tallest building in the world. And if you look at it from bottom to top, I'll highlight there are these different platforms that you can see staggered as a function of height above the ground surface. And if you look now down on one of these platforms, these are all solar panels, and each of these solar panels is being used to capture solar radiation, and all of the hot water used within the Burj Khalifa is heated from cold to hot temperatures using that solar radiation. People also might be familiar with using solar radiation to warm water for a pool, and in this case the way it works is on top of a roof shown on the left. If we look at a blown up image on the right, these are black pipes. Black absorbs more incoming solar radiation than any other color. And so these black pipes absorb the radiation from the sun, and the pool water is piped up the pipe through all of these pipes here, and then it's returned to the pool after being heated. So again, there's a cost in terms of having to pump the water, but heating the water is effectively free. When you drive around or fly around the world, you increasingly see lots of solar being used. This is a photograph taken out of an airplane landing in Phoenix, Arizona, and I'll highlight, if you look at the rooftops, you see many of them covered in solar panels. Phoenix is a city that on average for much of June, July, and August has temperatures that exceed 43 degrees Celsius or about 110 degrees Fahrenheit. And so in the middle and late afternoons and early evenings, air conditioning bills are extremely high. So what a lot of homeowners and businesses do is they pay the capital cost to install solar panels on the roof. And during those times of the day when the temperature is hottest and the air conditioner is running the most, that's when energy companies tend to charge the highest per kilowatt hour electricity prices. So what companies and individual owners can do is they can use the energy captured by these solar panels to offset the amount of electricity they have to buy from the grid. And you see this throughout northern Arizona and in a number of other cities around the southwestern United States. Here's a coffee bean similar to a Starbucks, and you can see each one of these tables that has outlets at the base. Each one of the tables has solar panels at the top, so they're not connected to the grid. They're simply capturing incoming solar radiation in real time and converting that to electricity. Here's the Whole Foods flagship store in Austin, Texas, and you can see the roof is fitted with solar panels, and you can see they face in different directions. The solar panels here on the lower part of the photograph, they are tilted to face east, so they capture morning sunlight through the middle of the day. The solar panels here in the back of the photograph, they face south, and so during the middle of the day to the late afternoon, they maximize the amount of solar energy that is used. Now, solar panels work very simply by using a number of different natural resources to convert the photons from incoming sunlight, or let me restate that, to use the photons from sunlight to actually knock electrons around within a solar panel. And I'm going to show you a video now of here how this works, and all I want you to take away are the high-level aspects of how solar panels convert solar radiation to electricity.
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles, called photons, shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the n side, while the hole is drawn to the p side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet. Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity, and most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles. Which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a little way off.
So the takeaway that I want you to have here is that photovoltaic solar panels, all they need is incoming solar radiation. That's it. These N-type and P-type silicons, if you were to choose resources for solar panels, many of you may have chose silicon, which is the second most abundant element on Earth. Other elements that are used are phosphorus and boron, which are not mentioned in this video. But again, they're very simple once they are put into use. There's a second type of technology that allows us to capture incoming solar radiation and convert that to electricity. And this is not using photovoltaic solar. This is something called concentrated solar power. And when you look at the photograph here on the left side of your screen, you see a tower in the center, and all of these, what look like solar panels, are in fact mirrors. And all of these mirrors, some of them are flat, a majority of them have a parabola type shape, and all of these mirrors, which are referred to here in the lower right as heliostats, those mirrors, when the sunlight strikes the mirror, it reflects that energy towards what's called a receiver, which is at the top of the tower in the photograph on the left side of your screen. And that receiver then, it receives all of that reflected energy from the heliostats or mirrors. And inside of that receiver, there are different ways of capturing that energy to produce electricity. You could have water inside the receiver, and that water can capture the energy and be converted to steam, and that steam can then turn a turbine, which turns a generator that produces electricity. There also now are what we call molten salt receivers, and I'll show you a video of how those work. And those have now become batteries that allow you to capture incoming solar radiation during the day to store that energy in molten salt. There are some very large concentrated solar power fields around the world. This is one in the Mojave Desert in Southern California. And again, you can see in the photograph 1, 2, and 3 towers, and they are surrounded by all of these heliostats or mirrors. And when sunlight strikes the mirrors reflect that sunlight directly onto the tower, and those towers then convert that energy into electricity. Here's one in Spain, and I'll highlight a couple of years ago, I took this from a newspaper article, that in some portions of the summer now, Spain has actually gone to 100% of their electricity by using these heliostats and concentrated solar power. So here's a video about a new solar technology that has the potential.
Solar power uses thousands of mirrors to reflect and concentrate sunlight onto a central point to generate heat, which in turn is used to generate electricity. More than 10,000 tracking mirrors called heliostats reside in a 4 square mile field where they reflect and concentrate sunlight onto a large heat exchanger called a receiver that sits on top of a 550-foot tower. Within the receiver, fluid flows through the piping that forms the external walls. This fluid absorbs the heat from the concentrated sunlight. In this technology, the fluid utilized is molten salt, which is heated from 500 to over 1,000 degrees Fahrenheit. Molten salt is an ideal heat capture medium because it maintains a wider operating temperature range in liquid state, allowing the system to operate at low pressure for superior and safe energy capture and storage. After passing through the receiver, the molten salt then flows down the piping inside the tower and then to a thermal storage tank where the energy is stored as high temperature molten salt until electricity is needed. This technology leverages liquid molten salt as both the energy collection and the storage mechanism, which allows it to separate energy collection from electricity generation. When electricity is required by the utility day or night, the high-temperature molten salt flows into the steam generator as water is piped in from the water storage tank to generate the steam. Once the hot salt is used to create steam, the cool molten salt is then piped back into the cold salt storage tank, where it will then flow back up the receiver to be reheated as the process continues. After the steam is used to drive a steam turbine, it is condensed back to water and returned to the water holding tank, where it will flow back into the steam generator when needed. The result is a high-quality, superheated steam to drive the standard steam turbine at maximum efficiency to generate reliable, non-intermittent electricity during peak demand hours. The steam generation process is identical to the process used in conventional gas, coal, or nuclear power plants, except that it is 100% renewable with zero harmful emissions or waste. These plants provide on-demand, reliable electricity from a renewable source, the sun, even after dark.
So I just want to highlight a couple of things because they don't use the term baseload power, but the concept behind these salt concentrated solar power plants is that the salt is storing energy from the sun, and then we can use that energy stored in the salt. If the salt is 1,000 degrees, then we can exchange that energy or that heat transfer from the molten salt in red to initially room temperature water in blue, and that allows the room temperature water in blue to be converted to steam, and that steam can turn a turbine and turn a generator and produce electricity, which is identical to how we use nuclear and natural gas and oil and coal. The term on demand was used, and that's something that's extremely important. One of the criticisms people often hear about renewable energy, such as wind and solar, is that capacity factor. It's not always available on demand. So this is a new technology that offers on-demand electricity when customers want electricity in the late afternoon or the evening when they return home and everyone turns the air conditioning on, depending on where you live. That's when this technology can produce electricity. So this is a snapshot of the technology that the video walked through. And again, I only want to hold you to the high-level details here, but know also that these can be scaled. So these can be built such that they're small for a small number of homes in a remote area. And in this case, we're looking at a map of the state of Nevada, and this is a solar energy project known as Crescent Dunes, where it's being built and has the potential to deliver electricity to Las Vegas, a city of 2 million people. So again, with wind, we looked at where wind energy is most feasible based on wind speeds. And I just want to highlight here is a map for solar photovoltaic. So this would be that photovoltaic where incoming photons knock an electron out of its orbital, and then that electron flows around wires. In this case, the highest average sustained sunlight during the day, of course, is in the American Southwest, West Texas, New Mexico, parts of Colorado and Utah, much of Arizona, most of southern Nevada, and then large parts of southern and southeastern California. But I want to make the point that everywhere else on this map still has the potential to generate enough photovoltaic electricity to satisfy consumer demand in real time if we have batteries or if we had salt concentrated solar power. A lot of people may have heard about Germany, and Germany has been among all countries on the planet leading essentially leading the world in renewable energy development. If we look at the colors here, I should have pointed this out, they correspond to kilowatt hours per square meter of land surface. So again, a square meter is about 3 feet by 3 feet, a little more. The brighter colors towards red are more kilowatt hours per square meter, and the purples are less. And I just want to highlight that everywhere in the contiguous or lower 48 states has more solar potential than Germany. And if you do the math, as you have done now for Southeast Michigan and the University of Michigan's Ann Arbor campus, there is more than enough incoming solar radiation in terms of kilowatt hours per meter square that the entire United States could power itself for electricity and also generate excess electricity for battery electric vehicles. So what are the challenges with solar and wind as electricity resources? The biggest is intermission. And intermission is shown here, where we have on the y-axis, we have the normalized hourly average energy, And this is for data from the summer of 2012, but assume that they're constant for now. And then we have on the x-axis a 24-hour day, so from roughly 1 a.m. or midnight on the left to midnight again on the right. Now, in blue is energy use. So think of that as your consumption and my consumption of electricity. Notice that it's low when we're sleeping, but it still is in the background. It then starts to climb when we wake up. Notice that it peaks in the late afternoon, early evening, and then as people transition to nighttime and go to sleep, energy use declines. Now, solar is shown here in orange with the triangles, and this means the amount of incoming solar radiation that we could use to generate solar electricity. Obviously, at night, there's no sunlight. The sun starts rising about 6, 7 o'clock in the morning, depending on where you live, and the sun continues to provide incoming solar radiation that we could use to generate electricity. It peaks in the early afternoon, and then the sun starts to set, and we can typically see at or after dinner, again, depending on the time of year, we move back into nighttime. So this upside down U-shaped curve represents over a 24-hour period of time when we have the maximum amount of sunlight. In red, with the boxes or squares, that is wind. Wind generation potential is highest at night. It tends to decrease during the day, and you can see it has a minimum during the early afternoon hours, and then it again increases as we return to night. So one of the things that we can see when we look at this figure is that wind and solar have the potential to complement each other. When solar is low, wind is high, and when solar is high, wind is low. And notice that when wind is high here on the left side, the amount of wind energy that we can generate, it is more than or it exceeds the energy used by humans. And again, over here on the far right side, we can see that the amount of wind energy exceeds the energy used by humans. If we look here in the late morning around noon, we can see the amount of solar that can be generated exceeds the amount of use. But the challenge, and this is the intermittency, is notice here, the blue for energy use exceeds both solar and wind. And again, over here in the mid-morning hours, the energy use exceeds the amount of real-time electricity that can be generated from solar and wind. And you can play various technology games of sizing extra solar and extra wind so that you could actually increase the sum of solar and wind. And this is something that engineers work on all the time. So when you hear about solar and wind, it's not just that solar doesn't work when the sun doesn't shine and the wind doesn't work when the wind doesn't blow. It's the relationship between the maximum amount of solar and wind electricity that we can produce relative to how much is actually being used by humans at any one particular time. That is something that engineers are trying to address. And that video I showed you about concentrated solar power, that would be, for example, in this part of the graph and this part of the graph, that's when we could use that molten salt to produce electricity in real time. If we think of wind, here is a histogram for wind over the year 2011 in the state of Wyoming. The y-axis is gigawatt hours, and all I want you to see here is that on a 24-hour basis, wind is fastest at night and slowest during the day, and over a year, wind tends to be highest during cold months and lowest during warm months. So again, this is an intermittency challenge that would have to be addressed by oversizing the amount of wind so that you can satisfy demand in the summer, and then in the wintertime, you either don't spin the turbines or you capture that electricity and store it. Here we've got another snapshot of intermittency for data from Texas. This is hourly wind generation for a period of time in March 2014. And again, all I want you to see over this roughly 30-day period of time, lots of wind if you look lower left. So this is in megawatts. So notice that the peaks and troughs, they would affect the ability of the local energy producer to provide electricity. So this issue of intermittency is definitely something that is a major challenge for renewable energy in the form of wind and solar. What about economics? I showed you earlier the capacity factor for wind and mentioned that the cost now for wind is comparable to natural gas and/or cheaper than natural gas. In many markets in the United States and around the world, wind is the cheapest way of generating electricity. The capacity factor for solar right now for commercial scale available solar photovoltaic panels is just about 30%, which means that over the course of a 365-day year, solar photovoltaic panels can generate electricity 30% of the time, which means that 70% of the time they're not generating electricity. Notice here's the levelized capital cost, which you learned about in a previous module, the operations and maintenance. Notice there's no fuel costs. So the total system levelized cost of electricity is more expensive than wind, but not by many dollars. So now in many parts of the world, a combination of solar and wind are cost competitive and in many places the cheapest way to generate electricity. The challenge is intermittency and storage of that electricity when the sun doesn't shine and the wind doesn't blow. If we look at two figures here, I just want you to get a sense of how the economics of producing wind and solar electricity have changed in your lifetime. Over the last decade, wind energy production has decreased about 67%, and utility scale solar has decreased 86%. And that's buried here in the data where we've got the bar and whiskers to indicate low and high and average prices. All I want you to see here is that in your lifetime, the actual cost of generating electricity using wind turbines and solar panels has effectively plummeted, which makes them economically competitive as energy resources. And we see that in a number of different markets. Here I'm just comparing the LCOE in dollars per megawatt hour, which is the data on the y-axis, since the year 2009. And if we look at wind and utility scale solar, as of 2017, if we look here lower right, they were the cheapest way to generate electricity. Cheaper than natural gas combined cycle in green, cheaper than coal here, and cheaper than nuclear. So this is why we see states in the Midwest where people will tell you they're opposed to renewable energy. The facts tell us that they are not. And the reason they're not is that if wind and solar can be used to generate electricity at a lower cost than any other technology, and that means the monthly bill that you get for electricity is lower, everyone is cheap, and everyone wants cheaper energy bills. When we look at wind energy potential, I showed you the change from 1999 to 2020. And again, all I'm highlighting here is potential around the United States. Without getting into the details, I just want you to know that the combination of wind, and again, this is wind potential at 80 meters, so about 200 feet above Earth's surface, wind energy potential and solar energy potential is enough to satisfy total demand plus battery electric vehicles. And we can see this in terms of the amount of electricity that we consume in the United States. So this is from 1975 through 2017. These are kilowatt hours in billions of kilowatt hours on the y-axis. And all I want you to see is that if we take the total potential wind energy times a capacity factor for wind, we can generate more energy, here specifically more electricity, than we consume. And this is something that even our current Republican administration in Washington, D.C. has become a fan of. So Trump, very quickly after he took office in 2016, 17, and 18, he has now directed the Department of Interior, and the Bureau of Ocean Energy Management, that same entity that regulates offshore natural gas and oil leases, he has directed them to increase the number of leases for offshore wind energy because they boost domestic energy production, and the key here is domestic, and they increase jobs. The second challenge is transmission. I showed you in a previous lecture all of the oil and gas pipelines around the United States. Now I just want you to picture electricity pipelines around the United States, which in reality they are. All of these lines here in the American Southwest and Western states and Rocky Mountain region, one of the challenges with wind and solar is that the significant abundance of wind and of solar may not correlate with population density centers, so there would need to be new transmission built to carry that energy to population density centers. If we look at wind speeds here off the coast and in the Great Lakes, imagine having an infinite number of wind turbines floating in the Pacific Ocean off of the west coast, and the Atlantic Ocean off the east coast, and the Gulf of Mexico here, and the Great Lakes. We would need to construct transmission lines to get that electricity to people in population centers. But this is something that we know can be done, and it's also something that's economic. So here is one example of a private company who are building a 3,000 megawatt wind farm in south central Wyoming near the town of Rawlins. And they are constructing a high voltage transmission line that will carry that electricity all the way to Las Vegas, where it will literally plug into the existing electricity infrastructure at the Hoover Dam, which I've shown you and talked about in the hydroelectric lecture and in one earlier lecture. And the reason that they can carry that electricity economically is they can then sell that electricity to the 2 million people in Las Vegas. They can also tap into the market that ultimately reaches Phoenix, and they can tap into the Southern California market. So this is a private company who are doing this because of the economics. If we look around the country at where wind farms are located and where wind farms and solar farms are being proposed, you can see here the number of business plans around the country that want to develop renewable energy infrastructure. And this is something that most economists predict will become the norm around the world in the next 1 to 2 generations. Because wind and solar, once you build the energy infrastructure, the fuel is free and they are as close to zero emissions as possible. The transmission lines will be built, and this is a graphic proposing connecting the dots. So if we look at wind farms around the US, we will build the transmissions to connect them. We've talked a little bit about energy storage in one of your modules where you looked at battery electric vehicles, and I had you use the Tesla Mega battery in South Central Australia and price that out in one of the most recent modules. So again, back to this graphic I showed you a few minutes ago, where energy use exceeds the amount of real-time wind plus solar. Batteries are also becoming cost competitive, and as batteries scale up, meaning more batteries are being used throughout the world, they will become even cheaper as a way to capture and store electricity. So the last few minutes of the lecture today, I want to talk about resources, which you focused on for Module 9. And remember that if we think of fossil fuels as resources that are finite, when we think of solar panels, all of the words here in black are resources that are used and embedded within solar panels or the infrastructure to build solar. And all of the countries here are where we source those resources. So for many of the lectures in the first part of the class, I focused on the metal copper, which we extract from the mineral chalcopyrite. And copper is used for the wiring. It's used to transmit electricity. It's also used in the thin film solar cells. All of these resources have to be mined somewhere to produce solar. The same can be said for wind, where we can see all of the various resources and all of the countries where we mine those resources. And I've mentioned that the rate of increased consumption of copper exceeds the rate of population growth around the world. We consume on average now about 300% more copper per year than we did in 1960, but we have plenty of copper in the ground to build a wind and solar infrastructure globally. Among the metals that are extremely important for all types of technology and also for solar panels, because solar panels and wind turbines, because magnets are used. Among the metals that we need are rare earth metals. These are metals that effectively in 1960 we didn't use at all, and we can see today that we use on average several thousand more percent than we did in 1960. Now, we can look also at steel. We also know that steel comes from iron. I mentioned the country Liberia, which is a major natural resource for iron and depends heavily on the export of that iron and the resource rents. One of the biggest concerns with renewable energy technology is the source of the rare earth metals that are necessary to build those technologies. So here is a figure with data from 1950 through 2017. And the blue here is the production of rare earth elements in the United States. The red here is the production of rare earth elements in China, and all other countries combined here are in orange. China right now as a country produces between 90 and 95% of all rare earth oxides that we consume in various technologies around the world. And there has been a growing concern by the U.S. Congress and a number of countries, not necessarily a political concern, although that does play a role, but a concern about having a single source for the rare earth elements that make renewable energy technology possible. There also is a concern by many environmental groups about the degradation associated with rare earth element mining in China. And I'm going to play a video now to give you some sense of this issue.
Rare earths are 17 obscure chemical elements whose sales add up to less than $2 billion a year, but are found in a wide range of gadgets and consumer goods, including the hybrid car and wind turbines. At a Metal Events Rare Earths conference in Hong Kong, industry experts such as Nicholas Curtis gathered to discuss a sector that has been thrown into the limelight this year.
Governments have now taken very strong public policy positions on industries that they want to stimulate. And many of those industries they want to stimulate are green industries. And those green industries require rare earths.
China, which accounts for around 97% of global supply, has recently imposed tighter controls as its booming economy looks to safeguard supplies. But global demand is also climbing fast, leading to projections of a 40,000-ton annual shortfall by 2015. Molypore CEO Mark Smith says the supply-demand mismatch is causing great concern to other countries.
Well, the rest of the world wants iPods and cell phones and iPhones and hybrid cars and compact fluorescent light bulbs. And then you couple all that with the policy decisions that the various governments of the world are making to try to improve the environment and lower CO2 emissions. You couple all these things together and you have a potential for a very serious supply and demand problem.
As China's industries begin to consume most of its own rare earth production, companies are seeking to secure reliable reserves for themselves outside of China. However, new mines take massive investment and are set to encounter tougher environmental regulations from governments. Stephanie McIntyre, Reuters.
So I'm sorry for the quality of that video. It didn't play super well. But I just want to restate something that she said towards the end, which is that as China consumes more of the rare earth elements they mine, there is growing concern. Now that video was from 2014 and they predicted a shortfall of rare earth element production by 2015. That has not happened. So just to let you know that China has increased production over the last 5 to 6 years. But remember back to the lectures where I talked about the theoretical economic growth of a country. When a country is young economically, they mine and export the resources. Then they become a manufacturing economy, and then they transition to a service economy. What has happened in China in my lifetime and your lifetime is China has mined the rare earth elements. Historically, all of those rare earths were exported to other countries where the technologies were built, and China in the last few years has started manufacturing products with those rare earths within China. So we see this economic transition happening in China in real time. Now, back in Module 1 for discussion, you looked at a Green New Deal. And remember, a Green New Deal calls for 100% of U.S. primary energy to be replaced with renewable energy resources, including wind turbines, solar panels, and grid-scale battery storage. This requires mining. I often meet people who are major supporters of the Green New Deal, and I think that's wonderful. And then they'll tell me they also don't want any mining anywhere, anytime, ever. And you can't have both. If we have a world where we power all of our lives, meaning all of the primary energy we consume, using wind turbines and solar panels and grid-scale battery storage, it requires mining, and that mining has to be done using legislation that minimizes or reduces as close to zero as possible the environmental degradation associated with mining all of these metals. You'll hear people criticize wind because it kills birds. So I stuck this one in here just to give you a sense of the mortality rate for birds. At the bottom, you can see more birds die every year by hitting windows and or being attacked by feral cats and or being electrocuted on high tension wires than are killed by wind turbines, which are here on the lower left. So again, depending on where you get your news, you'll hear people say that wind turbines are terrible for the environment because they kill birds. It's true that wind turbines kill some birds, but if we really were concerned about birds and not killing them, we'd get rid of all of our windows. And again, just to highlight, this is something that all politicians get behind. Everyone is interested in domestic energy, no matter what country you live in. All politicians want to produce significant domestic energy, and they are focused on jobs. So even the Trump administration, despite what they may say on Twitter or Fox News, they are fully supportive of renewable energy because it's domestic and it creates jobs. So that was a high-level look at wind and solar, and I hope you come away optimistic if you are someone who wants to see growth of renewable energy. It is entirely possible to provide all of the primary energy that we consume by a combination of solar and wind.